Hello, friends. So, this is just a follow up lecture to continental drift the other day. This was more about plate tectonics and its history. So, when we left off, we were talking about the fact that I couldn't remember his name for a second. Good old Alfred Lothar Wegener had proposed this theory, this hypothesis of continental drift. He had all these great pieces of evidence, four solid ones that you should have in your notes. But he was missing a mechanism. He thought continents just kind of floated across the ocean floor. And everybody thought that the ocean floor was kind of flat, like a big desert. Little did they know. And they wouldn't know until this guy came along during World War II. This is Rear Admiral Dr. Harry Hess. Please write his name down. Dr. Harry Hess. Rear Admiral Dr. Harry Hess. He was a admiral in the United States Navy during World War II. He was originally a professor at Princeton University in physical geology, and a Navy reservist. So when he entered the Navy, they put him on a destroyer with the new sound or sonar technology they were developing to locate and map the ocean floor near shores. That way they could land safely and hunt down German U-boats. But Harry Hess, being a scientist and having an opportunity to study the ocean floor, well, he took it. And he discovered that the ocean floor was not flat, like everyone thought, but it was made up of mountains and ridges. And that it looked like there were very deep trenches and possibly huge mountain ranges. And after World War II, he took this same technology, went out to the Atlantic Ocean, and started mapping it, and found this huge mountain range, and that there was volcanic activity when he started examining the samples. And he coined the phrase, and it's very important you write this down, sea floor spreading. Sea floor spreading. And this is literally where the sea floor is opening up and pushing it aside. And he was able to start putting this evidence together to help explain this movement. And continental drift, well, it came back to the limelight, and people started to have these arguments about it. Then came this woman. Well, can I move this box? I wonder. Can I move this around? Oh, I can. I didn't know. I'm learning. This is Marie Tharp. All right. Marie Tharp, an amazing woman. She was an ocean cartographer and geologist. Now, at the time, she wasn't given the credit she was due because she was a woman. Thank God we've changed these things, and we still need to work on it. She really proposed plate tectonics and seafloor spreading. She really helped develop the theory and idea along with her colleague here, Bruce Heisen. You can see him over here in this picture. Here they are together looking at the map of the southern Atlantic Ocean floor that she drew by hand. Her ideas really started to put the puzzle together. They really started to show us things. Here's a copy of the North Atlantic Ocean floor bed that she drew by hand. Yeah, I said that. She drew this by hand from all the sonar data they collected. She took that data and transferred it into this. Mind blown. I don't know how you do that. It's incredible. So with this, they were able to really start putting the evidence together for plate tectonic theory and seafloor spreading, because they had to have a mechanism. Remember, this is what Alfred Wegener's theory of continental drift was missing. It was missing the mechanism for movement. And here was the first major piece. See this ridge down the middle of this? Can you see this? This is the Mid-Atlantic Ridge. Definitely write down Marie Tharp's name and the fact she was a geologist and created this map of the Mid-Atlantic Ridge. Now, this is a huge mountain range that runs right down the middle of the Atlantic, and it's volcanically active, which they didn't expect either. So here's how this works. They move myself, my little face down here. So at the Mid-Atlantic Ridge, what happens is magma is upwelling through the center, here and causing it to push up and make new volcanic rock and mountains. And this pushes the older stuff to the sides. So it literally like comes up, forms, pushes stuff out of the way. New stuff comes up, forms, pushes the older stuff out of the way. And Hess's data showed this. Marie Tharp's data showed this. Together with the maps, they were really starting to see how these continents were separating. Now, this wasn't accepted at first. People were like, this is crazy. These continents can't be moving because the ocean floor can't be moving. But it was. And it had been going on for billions of years. That this magma would rise up and form these volcanoes and push this aside. We know this to be true now. And that this is a little section of it here, and that it moves. Like it's not real nice and neat. Here we get what they call a transform fault boundary, where it slides past each other, and the divergent boundary is where it's opening up. So it's moving in these chunks and sections, and that's why if we go back to this map, you can see that it's not a nice straight line, that there are these breaks in here where it's sliding past each other. So we could really start to put this together. And then we started to gather this data. This is a diagram of the current layout of the magnetic field around the Earth. It's very, very simple. The magnetic field lines move from the south pole or the north end of the magnet to the south end of the magnet, which is now geographic north. Don't let this overly confuse you. Just know that the Earth, it acts like a magnet. Remember how we talked about that core, that outer core being liquid and kind of sloshing around the inner core? Is that too crazy? It's so weird to not have you guys here. That it creates this magnetic field that protects the Earth. It's like a magnetic bubble we're sitting in. So this is what it normally looks like between reversals, but we find that it reverses. Now, it's not a clear, neat pattern, and we don't know exactly what happens during a reversal or for how long. And if you were here, we'd probably have a million questions about it. We'd have to dig up and answer and think about. Right now, we're just going to move on through it. If you have questions, you email me. And what they find is that you could actually tell which direction the iron was pointing. Because remember, iron is magnetic. And these mafic-rich, or iron magnesium-rich rocks that were forming in this ocean basaltic divergent boundary. See, it's all starting to tie together, I hope. Igneous rocks, here they are, baby. It caused them to freeze that iron into the magnetic place. And when the next one's cool, if the poles are reversed and pointing the other way, the iron points the other way because it follows it. So when the field lines point north, the iron and the rocks point north. When the field lines point south, the iron points south. And you get this flip. And the thing was, the flips were identical on either side of the ridge. Either side of the ridge. Same stuff, like same amount of flip on both sides. Can you kind of see it? Like this is the positive here and here. And here's the negative or south pointing. Here's the north pointing. Look, here it is over here. Identical distance on both sides of the ridge in the same directions, which means it had to form at the, that's right, at the same time. Had to form at the same time. And here's another good one. So we have the youngest rock in the middle then, and the older rock in identical forms on either side of the ridge. So we start to have this timeline. Just like that. Yeah, it's that crazy. Just like that. That looks identical on both sides. So we have this timeline that's identical on both sides, and it tells us how long these have been separating and how long this has been opening up and at what rate it's been pushing apart. So we know how long these continents have been separating. And it's the same idea here. It's just a different image. So you have this come up. It's forming this new rock here, this purple, right? Well, look, let's go all the way back here. It starts here. Let's say it starts here. This green rock forms and then separates, and the brown rock, and the blue rock, and the purple rock. Can you see how it's moving it out to the sides like that? And it keeps pushing out. And in doing so, we have a time frame then and a rate. Because, distance equals rate times time. So we have this distance and we have this rate. So now we can know how much time? Big, huge discovery. Not only did we know the continents were separated and moving like Wegener had predicted 100 plus years before, now we knew, well, not 100 plus years, that ain't right. 1912, 1960, like 40, 50 years before. It was starting to be widely accepted now. Now we had a mechanism that made sense, and the evidence started to tie together. We had a way to tie the evidence together. That's what was missing before. That's why science is one of those things. So here we are today. These are the major plates. Where can I put my face so you can see all this easily? So these are the major plates from around the world. There's a newly discovered one over here whose name I don't remember. I just read about the other day because, I'm always reading about this stuff. I love it. Yeah, and this is how they're moving. Like some of them diverge here along the Mid-Atlantic Ridge. And look, see these arrows right here? These are where they converge or submerge. And the ones right here that point in opposite directions, that's where they're sliding by each other. Instead of like coming apart, slamming together, sometimes they slide by each other. That's right where California is, and you get that big San Andreas fault. All this ties together: volcanoes, earthquakes, mountain building, which leads us from igneous rocks and metamorphic rocks. I swear there's a reason behind everything we're doing. We're studying the whole Earth. Here it is, in plates. So the question becomes, what's a plate? And you need to write this down. You got to have this in your notes. A plate is one of the many rigid sections of the lithosphere that moves as a unit over the material of the asthenosphere. Yeah, I know I don't like to have slides with words, but you got to have this in your notes. It's just super important that you understand this piece of it. So please write this down in your notes. Write this down too. What is tectonics? It's the study of large-scale processes that collectively deform Earth's surface. So it's all these pieces together that are deforming Earth's surface. It comes from the ancient Greek word tectonikos, meaning to construct, to build. So it's literally how the Earth is rebuilding itself, and it's the study of how the Earth is rebuilding itself. So ultimately, we come down to this. Notice it's in red, and it's underlined, so it's very important you write it down. Plate tectonic theory. The theory which proposes or suggests that the Earth's outer shell, made of individual lithospheric plates, interact and produce earthquakes, volcanoes, and mountains. This is where it ties together. This is where we get our igneous rocks. This is one of the major processes that drive it. And through their collision and the heat, we build up a lot of heat and pressure and make metamorphic rock as well. So this is where a lot of the transformation goes on in those processes. And we're going to look at metamorphic rocks after we're done with plate tectonic theory. What else do I need to tell you? Oh, so here's a quick overview of kind of how it works. We're going to get into that in the next couple of days. This is where it opens up at that mid-ocean ridge. And this is where it slams in and slides down underneath in what they call subduction. There'll be a whole piece on subduction this week, next week, something like that. And it melts, it creates extra melting, and look at that, boom, volcanoes. And then we get convergence, which forms mountains. It's amazing stuff. You're going to love it. Make sure you write all that stuff down, go back through it, and hopefully I can figure